this implementation, we will be using NumPy, TensorFlow, and PyPlot libraries. So let's import them first, as you can see here in this part. Matplotlib is used to plot and demonstrate the data. In this part of the code, we are going to generate sample data ourselves. In this example, we choose the number of the samples, the number of the features, and the number of the clusters ourselves. But in real-world examples and problems, these specifications are imposed to the problem. Here we have chosen to have 200 samples, 2 features, and 3 clusters. And we have used the random function of the NumPy library to generate uniformly distributed points from 0 to 20, as you can see here. The NumPy values are stored in a constant tensor called samples. In order to begin, we need to have initial values for the cluster centroids. So we choose the centroids from the sample points by shuffling the samples and choosing the centroids from them. This is what we do here in this line. Here we have separated the coordinates of the data in order to see the scatter plot of the data. Then we need to start a session, as you can see here in this line. Now it's time to explain a little bit about what session means in TensorFlow. In TensorFlow, we first design a flow graph by defining variables, operators, and constants, and these definitions only show overall design of the problem. The flow graph does not occupy any memory and does not perform any computations. In order to start computing the algorithms defined and designed in the flow graph, we need to define a session. Since the session would store values in the memory and perform the computations, it must be closed when not needed in order to release the resources. If we start the session with the with statement, it is called the context manager, and it will close the session itself. But if we use the as default format, we are considering the session as a default one, and it also needs to be closed after running. Each graph needs a separate session, but one graph can use different sessions with different initializations. You can see that the centroids are also shown in this plot as the stars. In order to find the distances between the points and the centroids, we need to use the TensorFlow function subtract. The most important point here is to use the property called broadcasting. Since we need to find the distance of each point with 3 different centroids, in other words, centroids of 3 different clusters, we must use the expand dems function of the TensorFlow library, as you can see here, such that the subtract function understands that we are using the broadcasting property. By broadcasting, tensors of different sizes are managed, and we can easily save on computations. After subtracting the sample points with the centroids of each cluster, we find the summation of the squared values of differences over all features of samples, and find the cluster index that shows the smallest distance by using the argmin function. These are the implementations of what I just said and explained. Here in this part of the code, we have defined a function that updates the centroids according to the newly clustered data. By easily using the dynamic partition function, we would be able to partition the data according to the indices provided. Then we can easily find the mean values of each partition and update the centroids. This is the usage of dynamic partition function and finding the mean of the newly generated or updated centroids. This is the last part of the implementation. In a while-true while loop, as you can see here, we try to converge the clustering using k-means method. If the iteration count shows the beginning of the process, we must begin with the initial centroid values, otherwise the previously found centroids are used. Then we follow the same routine. We must find the difference between the centroids and the samples, as you can see here. Find the summation of the square of the differences over all features of the samples, and at last find the indices with minimum distance to assign the classes. These are all done in these lines. It must be noted that the while loop is stopped whenever the centroids do not change a lot. So we find the differences between the new centroids and the old ones and stop the loop if the total differences are less than 0.1. Here you can see the differences between the centroids of the 3 clusters. And here you can see the threshold, 0.1. We can change this threshold to any other desirable value. Here you can see the result, which show the newly computed centroids per iteration. And it also shows that the whole process has stopped after 6 iterations.